Hello and welcome to another of Mr. Francois's Fabulous Fun Physics Facts. So today we're talking about a relative motion problem, and what we are trying to do is figure out how things move when other things are also moving, or when we actually do consider the fact that other things are moving. So here's an example problem. An inconsiderate person is driving north with a speed of 10 meters per second. They throw an apple core out of their window west with a horizontal velocity of 7.5 meters per second. Because quote unquote they were done with it and didn't want it anymore. A pedestrian standing 4 meters from the road is hit in the face with the apple core, and assume there's no wind resistance at play in here. We want to know how fast the apple core is moving relative to the pedestrian's face. So the first thing that we would want to do really is we would want to make a little diagram here. So what we're going to do is we're going to put a little road here. Here's going to be our car. Okay, and I want to do this from the above view because I'm talking about north, south, east, and west, and the only way to really view north, south, east, and west is the fact that you view it from an above view. So it's moving north with 10 meters per second, right? And they throw a apple core out the window, and it's going to go forward at some diagonal version because it's going to the side there, but it's also going forward, and it's being thrown to the side with 7.5 meters per second west. And here is going to be our pedestrian, who is unfortunately going to have a very bad day. So it's going to hit them full on the face. So here's what we have to do. Okay, we need to find the velocity of the core relative to the pedestrian's face. Now, the pedestrian is not moving. They're standing on the side of the road, which means they have the same frame of reference as the Earth, which means that the velocity of the apple with respect to the Earth is what we want. And so we start off with the velocity of the apple, and what we know is the velocity of the apple with respect to the car. And in order to get rid of a frame of reference, you have to add the velocity of that frame of reference with reference to a new frame of reference. So what that means is we would have to add the velocity of the car with respect to the Earth. And this is something that we already know. We already know what the speed of the car is relative to the Earth. That's at 10 meters per second north. So we actually do have everything that we want to know. We have the velocity of the apple core with respect to Earth, because it is the velocity of the apple core with respect to the car, which is that 7.5 meters per second west. And we're adding that to our 10 meters per second north. And so when we add these together, because they are in direct directions, namely they are in one of the set 4 cardinal directions, we can skip over making the chart for this one and just make a triangle out of it. So we have our velocity north, and we represent velocities just like all other vectors as arrows. So we have 10 meters per second to the north, and then from there we start at the end where it ends up, and we're going to the west at 7 meters per second. And so our end result, the direction that it actually ends up going, is the combination of the two. And this actually is a spin-off of the 3, 4, 5 triangle. It ends up as being 12.5 meters per second, and I can show you how I got that. Because we know both sides of this triangle, and we want to find the third side, the hypotenuse, we use the equation a squared plus b squared equals c squared, right? Because it's a right triangle, and I know the two sides, and I want to know the hypotenuse, which I'll call c for right now. And just to prove that we are correct, let's do it out. So we have 7.5 squared plus 10 squared is equal to c squared. So 7.5 squared is 56.25 plus 10 squared, which is 100, is equal to c squared. So we have 156.25 is equal to c squared. So we have to square root both sides in order to get it. And the square root of 156.25 is, in fact, 12.5. And that's meters per second. Now, we're not done because I did ask for the velocity, right? If we scroll back up here, we see that is, in fact, I'm asking for, well, I did ask for how fast it was. If I asked for the velocity, I have to find out what it is. So you always take the angle of the inside where you started from, seeing that this is where I started from and went off from there. That's the angle that I'm looking for. And the equation that I use is that angle is equal to the tangent inverse of the opposite over the adjacent, right? And what we put into that is the opposite side, which is the 7.5 here, and the adjacent side, which is 10 meters per second here. The reason why they're opposite and adjacent is all about where this angle is, okay? This is opposite of my angle, this is adjacent to my angle, and it's not the hypotenuse. Okay, the hypotenuse, being the longest side, is always opposite of the right angle, right? Okay, so it's not the hypotenuse. I don't use the hypotenuse in this one. So my angle is the tangent inverse of 7.5 over 10. And if I put that into my equation, I end up with 36.87 degrees. Now, it's not complete because we don't have a reference for this 36.87 degrees. What we want is to be able to reference this. So let's take a look over here. Now, this was 7.5 meters in the west direction. This was 10 meters per second in the north direction, right? Okay, now this angle here is, again, describing something off of something, okay? It's always something of something else, and we want to be very specific. Now, we originally had it in the north direction here, and then we deviated from that by swinging it towards the west. So this is a angle that is actually west of north. Another way that you can remember it is it's always the opposite of the adjacent. The opposite side was west, the adjacent side was north, so it is opposite of adjacent, west of north. Okay, so that answers part A. Part B asks, how long does it take to reach the pedestrian after it leaves the driver's hand? Well, if our pedestrian is standing 4 meters away from the road where the driver throws it from, then what we need to do is we need to use our kinematics equation. Now, this is horizontal motion, so that means that there is 0 acceleration, okay? And I know my initial velocity, and I want to find my time, and I know my displacement, okay? Because my displacement for part B is 4 meters. I know my acceleration is 0. I know my initial velocity in the x direction. So my horizontal velocity, this is talking about westwards, right, is 7.5 meters per second. And I want to find out time. Well, this leads me to use my kinematics equation of delta x is equal to vi delta t plus 1/2 a delta t squared. Okay? Only thing is that our acceleration is 0, right? And I always advocate for putting in values ahead of time so long as you are okay with them and that they don't mess things up. So I always advocate for putting in zeros ahead of time because they make things nicer for us. So that's 0, so that means this entire term is actually 0. So in the horizontal direction, the only thing that actually works is that you have your displacement is equal to your initial velocity times time. And so I can rearrange this in order to get a nice equation out for time. I divide by my initial velocity, so I end up with my displacement divided by my initial velocity, which gives me time, which in this case means that I have my 4 meters divided by my 7.5 meters per second, and that ends up giving me a value of 0.53 when we round to 2 decimal places. Okay, so that's 0.53 seconds. So that's how long it actually takes to reach the person on the side of the road. Okay, and you have to come to grips with the fact that we know the horizontal distance here, the westwards distance. Okay, he's standing 4 meters out from the road, and we have to assume that's to the west because it got thrown to the west and he got hit in the face. And even though the item is traveling north as well, giving us that 12.5 meters per second, we only really want to know the velocity in the west direction because it is in the same direction as our displacement. You can only use a displacement with a velocity that is in the same or opposite direction as that displacement. Okay, so I've got that answer. Let me just box my other answer so that I have it all set and nicely pointed out. The last answer is how far ahead, the last question is how far in front of the pedestrian did the driver release it? So we're asking for, well, what is this distance here that I've now written in blue? I'm going to call it x, or I'm going to call it actually delta x, because it's another displacement. So I'm looking for that. I know my velocity in this direction, right? Because I know I was going forward at 10 meters per second north. And I know how long it takes. I know it's that 0.53. So, since in a horizontal direction, delta x is equal to vi times delta t, I can solve out what delta x actually is by plugging in my vi, which was 10, and plugging in my t, which is 0.53, and finding out that the driver actually released it 5.3 meters, because it was meters per second, in advance. Okay, so there is your example for relative motion. I hope that it's enlightened you, and I will see you next time in class.